purpose of this lab was to examine the motion of extreme rope sports and construct a model that parallels the motion in the lab with a spring mass pendulum. We can do this by analyzing a mass system and collecting data points from the motion. Utilizing Newton's first, second, and third laws, we can predict and compare the results to our observations. The system chosen was to include the mass, the spring, and the earth, so no energies were lost. To begin the lab, you first need to build a 1D model that emulates the simpler motion of a spring mass oscillation along the y-axis. Tracker was used to collect position data points and to construct a 1D Python computer model. Because the model utilized vectors, it was easy to modify the model to a 2D computer model. The mass was given to be 0.402 kilograms. The initial ball positions were updated from the Tracker 2D video. The period for the y and x axis were acquired by utilizing the data from the Tracker programming and averaging 5 data points and calculating the period. I utilized 1.525 seconds for the y-axis and 1.634 seconds for the x-axis. The x and y data points were imported from Tracker using the read CSV option in Python. This step included a database index and allowed Python to apply calculus to the project. The delta t time step was set to 1/2 of a second, and little gravity, 9.8 meters per second, was added to the code. Once the period was calculated, I solved for the spring constants. After solving, I determined that K was equal to 6.83 Newton meters. The relaxed spring length, L0, was calculated from the Tracker data by recording the high and low Y motions for 3 data sets and averaging the results to calculate the relaxed length of 0.123 meters. L hat shows the direction of length as it changes from longer to shorter. S describes the magnitude of the spring stretch or compression. The next set of code computes the energy systems for the lab. Kinetic energy is 1/2 the ball's mass times the velocity squared, which expresses that a moving object can do work and quantifies the amount of work that a moving object can do. This is often referred to as the transitional kinetic energy. Gravitational potential energy is the mass times the gravity times the y position and measures the amount of work that can be done when a mass is raised or lowered. If the mass is raised, we have an increase in gravitational potential energy, and the opposite if the mass is lowered. The spring potential energy measures the elastic potential energy as a result of deformation due to stretching or compressing of the spring. The amount of work depends on the spring constant, K, which refers to the spring stiffness. All 3 energies are measured in joules, a unit of work. As I stated earlier, our system includes the earth, the mass, and the spring, which demonstrates the energy principle. With this system, there are no lost energies to the surroundings, which can be shown by the delta sum of the 3 energies equaling 0. 3 lines of code were added to state the initial times for the 3 energy systems. Fgrav used the ball's mass times gravity as a vector in the y direction. Fspring used the spring's constant times the stretch times L hat, which controlled the direction of the force. Fnet was equal to the vector addition of Fspring and Fgrav. Ball.v utilized the initial ball.v position plus Fnet divided by ball.m times delta t, which was calculated for Newton's second law, which states that F equals ma, or A equals F divided by m. The next 3 lines of code updated the L, L hat, and S for the spring, which were needed to update the code and apply the calculus step required for the next while loop. The next 6 lines looked at the average kinetic, gravitational, and spring potential energies. This was done by comparing the final minus the initial part by the delta t calculation. The graph plot stated the order and the items to plot. The next 8 lines displayed the arrows and the scales that were displayed, F spring, F gravity, and F net forces. And the last while loop updated Python so that we could observe and compare our computer model to our observation. Because both are seen at the same time, it was easy to make comparisons to see how well we predicted the motion. What does this mean? Is the energy principle satisfied? Yes. As you can see, there is little deviation from the computer model to that of the observed motion. I did notice that there's a small deviation as the time frame increased. This could have been due to mainly two things. There was some loss of amplitude because it may not have been a perfect spring, as the mass could swing on the end of the hook, and a secondary harmonic may have been introduced, causing a vibration in the spring mass system. Also, to a lesser effect, there could have been some drag force. After calculating the period for the X and Y data, these calculations showed the horizontal pendulum motion in the X direction and the bobbing Y direction of the spring mass. These calculations have affected the spring constant calculation and made the spring stiffer in one direction than in the other,